So the next planet we need to talk about is Saturn. It's the second largest planet. It's 10 times Earth's diameter and 95 times its mass. It has an average density of 0.7 grams per centimeter. It's less than that of water. So its low density, like Jupiter, suggests that its composition is mainly hydrogen and hydrogen compounds. Now Saturn looks different from Jupiter, ignoring the rings. The temperature is low enough for ammonia gas to freeze into cloud particles that veil the atmosphere of the deeper layers. So the different color is due to all the ammonia gas frozen as clouds at the top of the cloud layer. Saturn is 10 astronomical units from the Sun and takes for 30 Earth years to complete its orbit around the Sun. Now, however, its surface gravity is only 7% higher than that of the Earth's. So our 180-pound guy is going to weigh about 190 pounds. The most striking feature is its rings, which we're going to discuss a little bit later. Now, Saturn also radiates more energy than it receives, but unlike Jupiter, this energy probably comes from the conversion of gravitational energy from falling helium droplets as they condense in Saturn's interior. The winds close to the equator of Saturn reach 450 meters per second, or up to 1,000 miles per hour, and it gets slower down at the poles. We have measured a magnetic field from Saturn, and we can see evidence of it in the aurora on Saturn. This is a Hubble Space Telescope picture taken of Saturn, and we can see the aurora on the northern and southern poles. Now in 1997, a joint mission from NASA and the European Space Agency and the Italian Space Agency was launched. The space probe called Cassini arrived at Saturn June 1, 2004, and it orbited Saturn for 4 years. It took a lot of great pictures, a lot of information, and you can go to the Cassini website at nasa.com, just search for Cassini, and you can see all the pictures and data that Cassini took during its 4-year voyage. That brings us to the next planet, Uranus. It's the first planet that's not visible by the naked eye, and so therefore it needed to be found. It was discovered in 1781 by William Herschel, who was systematically surveying the sky. He was looking at the sky, drawing a very careful diagram of the stars, and looked at another spot, and he came back and he noticed one star had moved. Now, it's small relative to Jupiter and Saturn, but it's 4 times larger in diameter than the Earth, and has 15 times the mass. It's 19 astronomical units from the Sun, so it's really difficult to study from Earth. But even close-up images from Voyager reveal a pretty featureless object. So at 19 AU from the Sun, it has an orbital period of 84 Earth years. It's 15 times more massive than the Earth, but it's only 4 times the size. So the surface gravity is about 0.8 that of Earth. So our 180-pound guy weighs about 140 pounds, and it rotates every 17 hours. Now, Uranus really looks blue, and that's because of the methane molecules in the atmosphere. Methane gas and ice are responsible for that blue color. Essentially, red light is absorbed by methane molecules and blue light is not. And so what gets reflected from the sun is the blue light. Now, its interior has a density of 1.2 grams per cubic centimeter and has a smaller size. So Uranus must contain proportionally fewer lighter elements than Jupiter and Saturn. However, its density is too low to contain much rock or iron. Its interior probably contains water, methane, and ammonia. And the size of the equatorial bulge supports the idea that the interior is mostly water and other hydrogen-rich molecules. It is currently not known if the core formed first and attracted the lighter gases that condensed on it, or the core formed by differentiation after the planet formed. So looking at a cross-section of Uranus, we see it has a layer of molecular hydrogen gas, then mostly water, and maybe a small iron and rock core. Now, one of the strange things about Uranus is it's tilted on its side. Its spin axis is tipped so that it lies almost in its orbital plane. The orbits of Uranus's moons are similarly tilted. We're trying to understand why, and the best hypothesis we have so far is that it was struck during its formation, and it splashed out the material that formed the moons. It could be gravitational forces could have tipped it, but we really don't know. We just know it's tipped on its side. So as it's going around at summer or winter, since it's tilted at over 90 degrees, one half of the planet is always light and one half of the planet is always dark, until we get to spring and fall where it's half and half, and then in winter we just switch the poles. And finally we get to Neptune. It's similar in size to Uranus. It's a deep blue world with cloud bands and vortex structures. It did have a great dark spot at one time, was its most prominent feature, but that hurricane, that storm, died out a few years ago. It had been established that Uranus's orbit was being distorted by some gravitational pull. And so two mathematicians, John Adams and Urbain Le Verrier, actually predicted where to look at it just by looking at the wobble in Uranus's orbit. And when people then actually looked at where they predicted it to be, sure enough, they found Neptune. Neptune is 30 astronomical units from the Sun, so it takes 165 Earth years for it to orbit the Sun one time. It's 17 times more massive than the Earth, and is about the same diameter as Uranus, so about 4 times that of the Earth. It rotates every 16 hours. Neptune's interior is probably similar to Uranus's, mostly ordinary water surrounded by a thin atmosphere rich in hydrogen and its compounds, and probably has a rock iron core. Its blue, like Uranus, comes from methane in its atmosphere. But unlike Uranus, Neptune has cloud belts. So it's like Saturn and Jupiter. It radiates more energy than it gains from the Sun. So the deep interior heat drives convective currents, which then lead, via the Coriolis effect, to visible atmospheric bands.